So this is a continuation of the other part one. Now verify DR and BDR adjacent and BDR adjacence. So to verify the OSPF version 2 adjacence, use the command show IP OSPF neighbor, and this commands. The state of neighbor in multicast network can be as follows: full or DR. Can be full or DR. So with full or DR, full. So we have full or DRs. So this is a DRR or BDR. DRR or BDR router that is fully adjacent with non-DRR BDR router. So these two neighbors can exchange hello packets, updates, queries, and end them. So it can either be DR or be the full or full BDR that it's connected to. It is connected to. There is a DR or BDR router that is fully adjacent with none. It's neither DR or this one, but it is connected to BDR. It's either connected to BDR or DR, but the other, meaning at one end it can either be DR, one end BDR or DR, but the other side connected to the DR others. That is what it means. That one end here, it is either DR or BDR, but the other side, it is DR others. That is what it means. Then we have full DR, full and then DR. The router is fully adjacent with the indicated DR, DR neighbor. And these two neighbors can exchange hello package and updates and then this. So for example, this one here, as you can see, full this, that it's DR, then the other side, DR neighbors, and then it is connected to BDR. Then we have them full BDR. This router is fully adjacent with indicated, BDR neighbor. Neighbor. So these two neighbors can exchange hello packets, and then we have two-way two-way or DR others. The non-DR or BDR router has neighbor relationship with non-DR or BDR. So this is the DR on both sides. This side, this side you have DR others, and then DR others aside, right? Or BDR. Sorry. Yes, this is the DR others. DR others, DR others. That these are not. It's neither BDR or DR. So the normal state of OSPF router is usually full. It is usually full. The router is stuck in another state. It is an indication that there are problems in forming adjacents. The only exception to this is two-way state, which is normal in multi-access broadcast network. So verifying DR, BDR others, of course you have to run this command, show IP OSPF neighbor, and then you will see. You have this, as you can see, this one, and then this is full DRs, but this one here, it is connected. When you look at this, that it is connected, one side it's DR, but it's connected to full. So in full, it's either, when you look at this full, but it's designated. So it is connected. This DR and then this is DR others. In other words, we can go with the DR and then this. So it is here fully connected to DR. Fully connected to DR. That is what it means. On then the default DR BDR election process, we looked at the three steps that the router in the network elects router with the highest interface priority. Highest interface priority as the DR. So the router with the second highest interface priority, it will be DR. But most of the time, the priority, it is 1. but it ranges from 0 to 255. If you set as interface priority 2 0, it will never participate. The one with highest priority number, of course, it's the one to, but the default, as you can see, the default priority for multicast, it is 1. So if it is 1, if the interface priority are equal, then the router with the highest router ID, now the router ID comes in. The highest router is elected as DR. So the router with the second highest, it is BDR. It is BDR. So the election process takes place when the first router with OSPF enabled interface is active on the network. If all other routers on the network have not finished booting, it is possible that the router with the lowest router ID can become DR. So for the election to take place, all of the routers, they must have actually, they must have booted first, and then the election takes place. But if one boots first, and then there is there is the actual possibility that the one with lowest router ID can actually be the DR than the other one with the highest router ID. So we have what called there DR, designated failure, and then recovered. So after DR is elected, it remains DR until one of the following events occurs. DR fails. Once DR fails, then BDR comes in and it becomes the BDR. It comes into a play and it becomes DR. So once this one here fails, the BDR, the backup, it comes into a play and it also becomes a DR. So in the case, let's say the OSPF process on DR fails or is stopped, then the multicast interface on the DR fails or is shut down. So those are the three events. Those are the three events that will actually stop the router from being the router designated router. So if DR fails, then the BDR automatically is promoted to DR. So the IP OSPF priority command. So the IP now, the default is 1, and the range is from 0 up to 255. If you use a 0, this one here, it will never participate in DR BDR election. It will never participate. A value there does not become this or the. So the example, how to use it, you call the interface, for example, this, the one that is partially. Remember, we had three, I think it was something like this, I don't know. Okay, let's use 4 like this. So you use those interfaces that are. So if it's part of OSPF like this one, and you change it from 1 and maybe to, then automatically this router, it's going to be, even if it has the router ID as 1, 1, 1, it will become the DR because of the priority on this interface. Yeah, you need to note that. So this is ISPF priority, it is this maximum. Then clear ISPF. Now we've changed this and then we're clearing the IP OSPF process. So if you clear it, then automatically it's going to again change. And now if you clear, then it's going to try. You will have actually forced that interface to go back through the process of electing the DR. This is packet tracer, determine DR and then BDR. So it's packet trace activity, modifying single area OSPF version 2. So to modify, modifying single area OSPF to modify. So in this Cisco OSPF cost metric, you can modify. But before you modify, you need to look at, we have what you call reference bandwidth. For the cost, it is reference bandwidth and then the interface bandwidth. That there is that reference bandwidth that is always stated there, it is a must. And then the bandwidth of the interface. So it is, when you look at this is the reference bandwidth, which is 100 millions bits per second, then divided by interface bandwidth still in bits per second, so that you get to the metric or the cost. The cost is the distance. So when you look at this, the reference bandwidth is in BPS. They are here. As you can see, it is the same route, but we have the default bandwidth. The default bandwidth now, this is the interface bandwidth. That for 10 GB, as you can see, 10 GB, it is what is the so this is this thing. So it will be this divided by this, and then you uh, this divided by this, and then you get 0.01. But of course, if it is 0.00 this, it can't be the cost. It has to be rounded off. And if you round it off, you're not going to have a 0. So it is a 1. So even when you look at this one here, that the limitation or the channel, I will know, okay, like the confusing concept is that this is 10 GB and then this is 1 GB. But when it comes to the cost, it's the same. We have 1 and then 1. Because they are in points, the points, so they will have to be rounded off. Then while we have 100, as you can see, so the reference, it's 100 bits per second, and then when it comes to the default bandwidth in per second, it is still, this is 100. So it is the same. So all this, the 100 MBs, then this, they all have 1. So don't get confused. You don't need to get confused when you look at the cost of different the interface types, that they do have the same cost. It's because of the standard that the cost, it can't be in points, and it has to be rounded off. With this one here, it is not rounded off. But the cost, it's the distance, it's not the speed. You need to note that. When it comes to the speed, of course, 10 GB, there's a difference with 1 GB, and then 10 MBs, and 100, and then 10 MBs. There is a difference in the speed, but in the cost, the distance, that is where there is no big difference. So here we have our OSPF accumulates cost. The cost of OSPF route is the accumulated value from one router then to the destination router, assuming the auto cost to reference bandwidth, which is 10,000, command has been configured on all the. Then the cost of the link between each router is now 10. The loopback interface, default cost of 1. That's cost of 1. So here we have 1, and then the rest in between here we have 10, 10. The loopback interfaces, we have 1. You can calculate cost for each router to reach each network. So for example, total cost router 1 to reach this network. Now which one is this network? 2.0. Where is 2.0? 2.0, it is this. For example, total cost from router 1. Where is router 1? So this is the network, the loopback interface. From router 1, then we expect one giving us 11, as you can see, it's this. If you use show IP route, are we going to get 11? So it is here on router, show IP route, then now the destination is this one here. And you can see metric, it is 11. Where is it coming from? The distance here, it is, this is the administrative distance, 1, 1. But the metric, it's the cost between the network from the source and then the destination. Have 11, and even here it's clear. Metric, it is this. Manually set OSPF cost value that you can deal with the cost. You call the interface IP OSPF cost 30. Interface loopback, this IP cost 10. So you can manipulate. You can manipulate. So after manipulating, let me see what we're going to have. That after manipulating, test the failover backup approach. As you can see, changed. Now we have this. So what happens if the link between router 1 and router 2 goes down? That you can simulate it by shutting down gigabit Ethernet, which is this interface, and verify router dated to use R3 as the next stop. So this one here, it is not on the course, but it is all about the. Okay, so we changed, we had the 30, which one did we change? There is on R1, then interface 00. R1. So here we have our, we change. So here we have, as you can see, the distance, it's this one. Here the metric we have 10. But where is the metric coming? Why is it that it's 11? Why is it that it's 11? 11, it's from here. It is just from here because we have this and then this one here. So now when it comes to the next page here, we are changing router 1 G001. Where is router 1 G001? Which is this. We're manipulating it to um, 30. So meaning that now this one here, it is 30. So if it is 30 and then we disable this interface, of course it's not going to use this, it will use this. So it will be 30 plus this, 30 plus what? 30 plus 10, then plus 1, which is this, totaling to 40, 41. Is it what we have? Let's see. So, but which network are we trying to reach? So the next stop here, it will be 13. We're trying to reach which network? 10, 10, 2. 10, 10, 2. 10, 10, 2, which is 10, 10, 2. This, we have this. Here, this one is coming from. Okay, we can actually see what happens if the link between R1 and R2 goes down. You can simulate that by shutting down the gigabit Ethernet 00, which we did to verify the routing table update. Use R3 as the next stop. Notice that R1 reach R1 can now reach 10. This is it, 10.1.1.4 with 11.4, which is this network through R3. The cost value is this. I don't know why we are having a 15. The cost. Then via this. And then this one now. I don't know. Maybe they added this, but if it's from this. Oh, it's actually we're trying to. Anyway, I think even change this. So here we have this like this. So that is how the metric is actually generated, because as you can see, even this, so we have this. That's the reason why we have a 50. So OSPF version 2 hello packets are transmitted to multicast address, which is this. The hello packets are transmitted to multicast, and multicast address is this one here, all OSPF router. So for router, it has to be 5. Then for all nodes, router that are all node this other NDI, it has to be 6. So hello packets are not sent on interfaces that are set to passive. To passive. So the dead interval is the period that the router waits to receive hello packet before declaring the neighbor down. So before it declares that the neighbor is down, it has to wait for dead interval time. If the dead interval expires before the router receives the hello packet, then OSPF removes that neighbor from its link state database. It's going to remove. So if it fails to coordinate with it or to reach it, then it's going to be removed from its link state database. So the OS, the router floods a link state database with information about about the down down neighbor out of all OSPF enabled interface. So Cisco uses default of four times of hello timer. So this is 40 seconds of multi-access and then point-to-point network. So Cisco uses default of 4 timer hello. So if it is 10, then it has to times this 4 and it gives you 40. This will be the time that it has to wait before it declares it as unreachable network. When you look at this, to verify hello and dead, this is the command show IP OSPF interface on this. And then automatically you will see the hello, it's 10, and then the dead is this. Waiting time is 40, which is the same. Transmits 5 or basic rise, which is 40. So this every 10 seconds, it has to send the hello packet. So if the router waits 4 times without receiving hello time the hello packet, then the router, it will remove that neighboring device from its routing link stage database shareable. So verify hello timer and dead interval. As you can see, the state that is this on router 1, and look at this state, it's full connected with the other side, and then the address of those other neighbors. So if you want to modify, you go to the interfaces that are participating in OSPF, and then you call interface. So you call the interface, then under interface, it's IP OSPF, OSPF hello interval, maybe 10. Then OSPF date, it's 40. So on that point to point, the point to point, the hello, which is 10 and 40 date, they have to be the same. So if they are not matching, then of course it's not going to work. It's not going to work. Remember, we said the hello, if it is 20, then it's times 4 to get the dead time. The dead interval. The hello interval is 5, and then the dead interval, it has to be times 4. So the hello packets, hello packet intervals. So with OSPF version 2, hello packets are transmitted to multicast address, which is this, and here 224, and then this for all routers. And then when it comes to other devices on the network, 6. So every 10 seconds. So every 10 seconds, the hello packets are sent in. So this is the default timer value for multicast access and then point-to-point network. So hello packets are not sent on interface set to passive. So the interfaces that are set to passive, then automatically the hello packets are not set there. Then we have the dead interval is the period that the router waits to receive hello packets before declaring the neighbor that it's down. If the dead timer expires before the router receives a low packet, and then the OSPF removes the neighbor from its link state database. So in other words, the low timer, if it is 10, then the dead, it has to be 10 times 4, meaning that it has to be 40. Has to be 40. So verifying hello and then dead timer can run this command. This command show IP OSPF interface. Then automatically you'll be able to see the error timer, which is this and then this. And then that. So in the scenarios where you have point to point, here, if it is 10 and then 40 as dead, it's this, then dead, it's this, then it has to be the same 10 and then 40 the same. This is 0 and then the dead. If not, there will be mismatch of those intervals. So to verify, still use this command show IP OSPF neighbor. If now this one here, it shows the neighbor that on router 1, which is this, then the neighbor it is 3 and then 2, and then the step, and then the IP address of those interfaces. So if you want to modify OSPF, the OSPF intervals, you can actually use this command IP OSPF. You call the interface, maybe interface G00, then IP OSPF hello interval, and if it is maybe 20, then the other one it has to be this, the dead interval, it has to be 20 times 4, giving us 80. 80. So you can use no IP OSPF dead interval or no IP OSPF dead interval command to reset. So if you are resetting, you just run this, but do not put the, do not just put no IP OSPF dead interval period. Yeah? Then modifying the interface, which is the same what we said. As you can see, this is the sample. This is 5, so it will be 5 here, then 5 times 4, giving us 20. Giving us 20. And then this is the packet tracer module where you have to adjust the reference bandwidth count, then the cost, the error timer, then verify the modifications are accurately reflected in the router. So the default route propagation. Default route propagation, it is all about, actually it is used in the scenario where you have more than one routing protocol. So here we're dealing with OSPF, but as you can see that it's the default static propagation. So here we have our reference topology, which is this, and as you can see that we have our loopback interface, which is this one here, and it's what we have here, that interface loopback 1, the IP address, it's here, which is this one here, it is stated on this, then the subnet mask exit, and then you use the default static route. We did it actually, we tried it out in module 2, sorry, not module 2, but semester 2, in the last chapters. You know how to configure the default static route. So after configuring default static route, we can actually propagate the default static route. Now we can have it within the router OSPF, so that router 2 is able to advertise the default static route that was created on router 2 to these other routers, router 1 and then router 3. So as you can see, it is here, and it's not part of the OSPF, because the OSPF it's covering this interface here, and then now this one here, it's static, but it is propagated within this router OS information or image. So once that's propagated on router uh, on router on router 2 where we configured it, this is how it's going to look like, as you can see here. So router 1, now it's going to look at it as a remote route, and this is how it is displayed, or how it is indicated how it is indicated there. So notice that the root source of R1 is 0 with the star E2, signifying that it was learned through OSPF version. Asterisk identifies this as the good candidate for default root. Then a true designation identifies that it is an external root. It's an external root. The meaning of E1 and E2 is beyond of the scope of this module. Here we can actually this is the packet tracer about propagation default route into OSPF, where you look at propagate a default route and then you verify connectivity. So verify single area OSPF. We can use this these commands, command show IP interface brief that will display the state of the interfaces, the IP address, are they up, all that information. Then show IP route for displaying the routing table. So the active route, routes from the source to the destination, from one router to this other, and then to this other router in OSPF. Then other additional commands for determining that OSPF is operating as expected, we include they include show IP OSPF, show IP OSPF neighbor, show IP protocol, show IP OSPF, show IP OSPF interface. They are very crucial verifying commands. So once you're familiar with them, then you will be able to retrieve all the necessary information that you need from OSPF topology. Verifying OSPF neighbor, as you can see, it's this command, and you'll be able to have this information. This is the neighbor ID, the neighbor router ID is this one here, and then the state, and then the date timer. So as you can see, the date timer keeps on counting. Then verify OSPF neighbor. We have these two routers may not form the OSPF adjacency if the following occurs, that the subnet mask do not match. If the two here, the subnet mask here is not the same as this side, then the hello and then date timer, if they are not matching both. The network type do not match. If this side you have point to point, and then this side you have broadcast, still it's not going to work. There is missing or incorrect network command. If the network command that you've used this side, the network that you've used, that you've advertised this side is not the same this side, instead it's not going to, the OSPF adjacent will not occur. Verifying OSPF protocol suite, protocol set router ID, because this is router 1, this ID is this one here. Then we can tell the network where we have now the participating interface, loopback interface is 0, this, and then this. But here we need to look at the neighbor. The neighbors we have, as you can see, 3, 3, and then the 2, 2, 2. Then verifying the process information, show IP OSPF. You can see we have this, then the ID is this, and here. The area, it's backbone, which is area 0. Area 0. Shortest path first algorithm executes 4 times this. such information. And then interface settings, as you can see, show IP OSPF interface. So if you run that, you'll be able, it's up, line protocol is up, the internet address on this interface, it's here, the area is, the process ID is 10, the router ID is this, network type is point to point, and then the host is 10. The neighbor count is 1 in R1, the neighbor is point to point, the neighbor is so still we can use this show IP OSPF interface brief, as you can see. So we have this one, this, all this, the app, ID 1010 area, backbone, IP address, and the mask they are here. And then the cost, when you look at the cost, they are here. Change it somewhere, which is this information. Packet tracer verify. This you verify single. In this packet tracer, you complete the following: identify and verify status of OSPF neighbor, determine how routes are being learned in the network, explain how neighbor state is determined, then examine the settings for the OSPF process ID, and then add new LAN into existing OSPF. So all this information, I think I'm going to share all this information. Yeah, I will share all these packet tracer activities. Yes, so that is the end. Thank you.